As we've seen, we can learn a lot about the thermodynamics of phase transitions by constructing these diagrams for the molar Gibbs energy as a function of temperature with constant pressure, or conversely, as the molar Gibbs energy as a function of pressure with constant temperature. What I want to explore now is how to get around the limitations of these figures in which we can only look at temperature or pressure. We can't look at both of them at the same time. So I want to figure out a way we can take this information and summarize it in a way that will give us some new insights and perhaps some new information about a system. So the process that I want to follow in doing this will look something like this. I want to construct these diagrams. So in other words, construct a plot of G of t for constant pressure, just as I've done here on the right. So that'll be our first step. The second step would be to repeat for several pressures. So I want to look at what this looks like when I have several different pressures plotted along so that I can get an idea of what the variation is for those different pressures. And then I'm going to create a new plot that will basically tell me about the phase equilibria for different pressures and temperatures. So I want to see what they look like as a function of pressure and temperature. All right, now this is difficult to describe in words, so let's use the diagram that we have here to begin to illustrate what I mean by this. Okay, in this particular diagram, and I want to say right off the bat that this diagram is going to be representing a pressure of 1 atmosphere. I've got 2 points that represent phase equilibria transitions, right here and right here. Now, since this is a pressure of 1 atmosphere, this will correspond to a temperature, the temperature of fusion, which actually is going to be the normal melting point because it's at a pressure of 1 atmosphere. Likewise, this temperature of vaporization that's recorded here will actually be the normal boiling point. Now the whole idea is I want to draw different pressures on this diagram and look and see where the curves intersect and record those on a new plot so that I can get some comprehensive information about how things vary with both pressure and temperature. So in other words, I'm going to want to create a plot down here, and I'm going to draw this very slowly and carefully. And on this plot, I'm still going to have temperature as my horizontal axis, but I'm going to have pressure as my vertical axis. And just to give you an idea of the sort of thing we're going to be doing, I'm going to put a place marker here for 1 atmosphere. So that would correspond to something along this horizontal line. And when I plot these 2 temperatures down here, this is going to tell me part of the borderline. In the case of temperature of vaporization, it's going to tell me part of the borderline between liquids and gases, and for the temperature of fusion, it's going to tell me part of the borderline between solids and liquids. All right, but to learn more, I'm going to have to look at more different pressures. Now, I'm going to simplify this a little bit by assuming that the vapor and the liquid curves, that is this curve and this curve, are not going to change a lot when I change the pressure. So I'm just going to leave those curves there. The only one I'm going to change is the vapor. I'm sorry, I said the vapor curve. I meant the solid curve. The vapor curve is going to be the one that changes. So the first step is to look at some pressures that are lower. So I might look at one pressure that's lower, and it might come down sort of like this and curve down. And what this will do is introduce a new value for vaporization temperature at a lower pressure. So this is at a pressure that is less than 1 atmosphere. So I would plot it down here somewhere, and as I plot this temperature on down to the lower plot, I need to go to a lower pressure in order to capture exactly where that's going to be. So this is a little bit lower than my initial pressure of 1 atmosphere. Now if I go to another lower pressure, I might go to a pressure that goes right through the intersection of the other 2 curves. So I hope we recognize that that would be somehow representative of our triple point pressure, and this would be our triple point. Now the way I've drawn things here, it actually corresponds to the same temperature as the temperature of fusion, and to be honest, in real substances that often is the case. It's a coincidence here, and it doesn't have to be the case, but we'll plot it on down here so that our triple point is recorded at a lower pressure yet. Lower pressure than the one that we just plotted. So this is our triple point here. And I'll leave it at that. Okay, we might go to a further lower temperature, go to a lower pressure, a pressure that's actually below the triple point pressure. And if we do that, we'll find that there is a phase transition that occurs between the vapor phase curve, which is this purple curve, and the solid phase curve along here. So this new critical point, this new phase equilibrium is going to be between the solid and the vapor, and that represents a sublimation. So when we go down here to a lower pressure yet, now we're at a pressure of sublimation. So you can begin to see that we're constructing points along this graph in the bottom, and they don't all lie along a line, and they shouldn't, but these points are going to help us map out where these phases exist in a space that includes both pressure and temperature variation. Now let's go to some higher pressures. So we might have a higher pressure, that goes down like this, in which case there will be a much higher temperature of vaporization. We might go to a higher pressure yet, and I'll say that this pressure represents the critical pressure, and just for convenience I'll say that it intersects the liquid curve somewhere down here, so that would be our critical point. So this pressure is the pressure of the critical point. And so now these two represent higher pressure, so they're going to be up in this part of the pressure regime. And if I plot this one here and plot this one up here as the critical point, all right, this is giving me now a pretty full set of curves that I can, can use to construct these boundaries between the various phases. So now if I begin to connect the points, I've got a triple point here, so let me label that. And from below the triple point, we're going to come up and hit that triple point right about here. Okay, so what I have along this boundary is solid up above and to the left and vapor down and to the right. So this is a coexistence curve between the solid and the vapor. I'm then going to have a coexistence curve that comes up here, and I didn't draw this very well, but I hope you'll allow some artistic license here. Another coexistence curve that represents the coexistence curve between a liquid above the curve and the vapor below the curve. So along this curve, I have liquid and vapor in equilibrium with one another. Then I'm going to have yet another separation that will come up like this that will represent the separation between the solid and the liquid. So this is the solid-liquid coexistence curve. So what we're seeing is that by plotting these points for various pressures in the diagram for molar Gibbs energy versus temperature, we're actually constructing a map, if you will, and that map is telling us something about the regions in which we're likely to find the vapor, where we're likely to find the liquid, and where we're likely to find the solid. All right, so they're mapped out in these various areas on this diagram. All right, so this diagram, by the way, is called a phase diagram, because it's a diagram that tells us where we can find the various phases for a substance in terms of the pressure and the temperature. Now I want to focus on one particular part of this phase diagram just to illustrate one other thing. All right, now the part I'm going to focus on is the part right around the triple point. So we're going to have the triple point here. I'm going to have the solid gas, solid vapor coexistence curve coming up to it. I'm going to have the liquid vapor coexistence curve coming out of here. So let me label these things so that we know where we are. And one of the things that I want to highlight on this is that this curve, if we were to continue it, would go up this way. And this curve, if we were to continue it, would go out this way. Now, these two continuations are really fictitious. These are unstable extensions of these phase coexistence curves. But you can think of this as representing, if you will, a superheated solid, because it's an extension of the solid vapor coexistence curve. And you can think of this as being like a supercooled liquid. Now my main point for drawing these things is that when we have a coexistence curve with a vapor, what this is really representing is the vapor pressure of that phase. So I'll call that P sub vape. So this curve down here would represent the solid vapor pressure. And the curve up here would represent the liquid vapor pressure. So these continuations of these curves might indicate what the liquid vapor pressure would be if we were down in here, and this might indicate what the solid vapor pressure would be if we were somehow up in here. The whole point of showing this, though, is to indicate that the vapor pressure that is the highest actually represents an unstable phase. So if there are two vapor pressure curves that are coexisting at the same temperature, and this is temperature along here and pressure along here, then it is the lower vapor pressure that is the more stable. So lower P vape identifies the stable phase. Now, one way we can think of this is that if these curves actually, if the higher vapor pressure curve, if the higher vapor pressure phase actually generated vapor, when that vapor condensed again, it would condense into the lower vapor pressure phase. So that's why it tends to collapse down to the lower phase, and that's why this phase is going to be, in general, the more stable. Since we no longer have the Gibbs energy to show us which one is the more stable, this is a useful guideline in case we ever have any doubts.